Hello. Today we are discussing concavity and sketching a graph using first derivative and the second derivative. So let's have a look at this graph, three graphs in three different colors. So the first one is red. The red actually is a cubic function. So I put that cubic function is 1/3 of x to the power 3 minus x squared minus 3x. That's a red. Second graph is in blue, so which is quadratic, which is a derivative of the y. So the differentiate y, so you can see which is x squared minus 2x minus 3. So if I differentiate y, so when I draw the graph, it's turned into a parabola. Lastly, this green straight line is the second derivative of y, so which is differentiate the first derivative, so which is 2x minus 2. So that's the straight line. So those three graphs we put onto the same graph, same Cartesian plane. So let's have a look at the relationship between those three graphs. So first we will see, let's see, I'm going to mark some dots. So you can see this is the first, this is a turning point. So on the first graph, we have, so I can use, probably I'm going to use red. So I'm going to use a red color. So I'm going to use red. So this is my maximum point, maximum turning point. So this is the original function, so the cubic function. This is the minimum turning point. So we can see if I draw a line there, across a vertical line down the bottom, so you can see if I change to blue color, so you can see there is those two dots. If I draw vertical, so the line go down, vertical. So that's those 2 points corresponding to those maximum and the minimum point. So this one we will see, those are the when the derivative equal to 0. So that's why we call second derivative 0, isn't it? So that means when the derivative equal to first derivative equal to 0, so the graph achieves the maximum or minimum points. So let me just put into a table so we can discuss. So the relationship between first derivative and the graph, we can use this table. So we call if y equal to 0, which is first derivative equal to 0, so the graph achieves either maximum turning point or minimum turning point. So this is a situation number 1. Now let's have a look at when the first derivative. So if I using my blue pen to trace this section here, so this is the first derivative less than 0 because it's below x-axis. So you can see when a y less than 0, so our red graph, our original red graph, if I'm going to change to red color, so you can see between that section, the graph, the original graph is go from up downwards. Can you see decreasing? So the graph is down, so the decrease. So therefore, the graph, original graph is go down. And on the right, if I put first derivative positive, so let me say, what about on the right hand side, first derivative y dash more than 0, greater than 0. Sorry, I'll just write a bit of neater. So this is more than 0, greater than 0. So that So that means if we look at the greater than 0 in this section, so this section here and this section here, and you can, so this is a y dash greater than 0. So then if you look at the red line, so you will see my original red line, or the graph, the original graph is, instead of go down, is go up. Can you see on this section here, the graph is from left to right, is go up. Go up. And this section is also, because that's the on the positive side, and that graph is go up as well. So therefore, we will see when first derivative is more than greater than 0, so the graph is increase. So this table is indicated relationship between derivative and the original graph, the whether it's increase or decrease or stationary. Okay, now we're going to discuss the next situation, which is the green line. So that's a second derivative. So I'm going to change to green color. So I'm going to draw another table into a second derivative on the right hand side. Again, we choose 3 situations. Okay, the first situation is y dash, double dash, less than 0. The middle one is double dash equal to 0. And the next one is greater than 0. So let's have a look at 3 sections. First, let's talk about the middle section. So let's say if I double dash equal to 0, which is here. So that's equal to 0. So when y dash equal to 0, let's have a look at the original graph, the red line. So if you look at the red line, I'm going to change again to a red pen. So you can see if I draw a line there, can you see at the original graph, it's this case, which is called, so you can see it's a straight line. It's not a stationary, but we call point of inflection. So what I mean by that means the graph is going to like something like that. So the point of inflection is it's inflect on this point. It's there's some other situations called horizontal point of inflection. So in this case, we call point of inflection. So point of inflection. All right. So this is the point of inflection. Okay, let's have a look at what about if the second derivative is less than 0? Can you see the graph? So we can see on this side, on this negative side of the second derivative, which is I'll trace that line. This is a negative side. Can you see the red line shape is like that? Can you see the shape is called, this is if the second derivative is less than 0. So this is we call concave. The graph is concaved. So I'm going to use red color instead of green. So I'm going to change to red. So the original graph is concaved, but we call concave down. Concave down. So this is a concave down. Now let's have a look on the positive side of second derivative. So I'm going to check on the positive side of the green line, which is above x-axis on this side. So you can see the red line is, can you see it's concaved, but it's a concave up. So not going to change to red color again. So the graph is concaved up. So that means, so this is, you can see we will be, so we go concave up. So this is a maximum turning point. Concave up is a maximum turning point, and concave down is a maximum, and concave up is a minimum. So you can see when I decide the second derivative, we can actually decide whether its graph is achieved the maximum stationary point or minimum stationary point. So this is a very important. So second derivative of -0, so which is less than 0 or negative number, the concave will be down, so will be maximum point. And second derivative greater than 0, so the graph, the original graph will be the minimum stationary point. So this is actually called turning point or stationary point. So this is a stationary point. So in the past, we use the first derivative to decide whether it's a maximum stationary or minimum stationary point. But now, once we know the second derivative, so we can easily to decide whether it's a maximum or minimum. So can you copy this two tables into your book? So that means you can use later on. So now I'm going to have a look at another example on the bottom. So I'm going to change to second example. All right, so this is another 3 examples here. So we have first, this is the original equation. So let me just using some colors. I'm going to use red color. So the first one is red color, which is the original function is y equal to x to the power 4 minus 4x to the power 3 plus 10. So you can see this, the first graph is we call quadratic function. So in this case, you have a point of inflection, stationary, but it's a stationary point of inflection. So it's a station, but it's a horizontal point of inflection. Can you see that? And this is another point of inflection. So we just point of inflection normal. So this is stationary or called horizontal. This one is minimum local turning point. So this is a minimum point. So we got 1. So that's 3 points. How they achieve those 3 points? So let's compare to the dy. So first derivative, sorry. So first derivative will be 4x cubed minus 12x squared. So this is the, again, you can see the points, the local turning point achieved when this is a y dash equal to 0, obviously. So when equal to 0. All right, now let's have a look at the y is a minimum, because if you look at the second derivative, y dash 12x squared minus 24x. So you can see this is the second derivative in here, this section here are positive. So if it's a positive, so that means this has to be concave up. Remember, when second derivative is positive, the original graph is concave up. All right, let's have a look at this. This one is another y dash equal to 0, which is first derivative equal to 0. So again, this is achieved to another stationary point. Can you see that vertical line here? So that, because y to 0, that's a stationary. But this stationary is not a maximum, neither maximum nor minimum, but it's called inflection because you can see it's inflect from this point. So you have a stationary, but it's an inflection point. So if you look at those two graphs, then what about this here? This is a second derivative equal to 0. So that means the original graph must be point of inflection. Remember, second derivative equal to 0, the original equation must be achieved a point of inflection. So this is a point of inflection. So there's an inflection here. So if I use tangent, that's inflected. And so if you look at the second, so that means if you look at this section here, so this is below the 0. So this section is y dash less than 0. Can you see this section is less than 0? And the graph is go down, so decrease. Then this go up, so graph go up. So this is a positive, so y dash positive 0. And again, this is a section here is again, so y dash less than 0. So the graph is go down. And if you could look at this one, this is another y dash equal to second derivative equal to 0. So if you go up, and this here is a stationary point. So whenever y dash equal to 0, and regional function will be station, will be inflection. All right, so this is a very good example of how we can see compare y and the first derivative and second derivative and using the sketch the graph. All right, so now I finish this example. So hopefully you'll be able to do some practice as your homework. So thank you for watching. I'll see you next lesson.